In this video, we're going to start talking about how we can calculate the pH of a particular solution of an acid or a base. So the process we go through for calculating the pH is going to be quite different depending upon whether we're looking at a strong acid or a weak acid. So this video is going to focus just same goes for strong and weak bases. This video is just going to focus on strong acids and bases and how we handle those. Because if it's strong, it's going to be similar regardless of whether it's an acid or a base in terms of the process. So what we need to remember is what it means for an acid or base to be strong. We know that means that it ionizes completely in water. So that essentially 100% of our acid or base particles are reacting to produce hydronium 2 hydroxide. So essentially the reaction that happens in water is going to completion. It's not establishing an equilibrium. It is going all the way to products. So since it's going to completion, we know that our acid or our base is being reacted away entirely to produce this ionized state. We can just use the stoichiometry or use our coefficient ratio to determine the amount of hydronium or hydroxide produced. So as long as we recognize the reaction that's happening and have it balanced correctly, that's all we need to do is use our coefficient ratio to convert from moles of acid to moles of hydronium or moles of base to moles of hydroxide, and then we can find the pH using those concentrations. So for example, let's calculate the pH of a 0.01 molar HCl solution at 25 degrees Celsius. The temperature isn't directly going to come into our calculations, but if we end up needing kW somewhere along the line, it does tell us that the value of kW is our usual room temperature value of 1 times 10 to the minus 14th. So since HCl is one of our strong acids, we know that it is going to ionize completely. So when this reacts with water, HCl reacts with water, and this reaction goes to completion. So we do just use the single arrow. The acid is going to donate H+ to water, producing hydronium, and that leaves just a Cl minus a chloride ion left behind as the conjugate base. So the concentration of our acid solution is 0.01 molar, 0.01 moles of HCl were put into each liter of this solution. In order to calculate the pH, we need to take the negative log of the hydronium ion concentration. So we need to figure out how much hydronium is produced by the amount of hydrochloric acid that was present in our solution. So this reaction, as I've written it, is already balanced. We have 1 mole of HCl to 1 mole of hydronium produced. So all we need to do here is that molar conversion, that we have 0.01 moles of HCl per liter of that solution. And there is 1 mole of HCl in our reaction, reacting to produce 1 mole of hydronium. So we will have the same concentration of hydronium as we did our hydrochloric acid to begin with. So now that we have our hydronium concentration, this value is all we need to be able to calculate our pH. So our pH is just going to be equal to the negative log of 0.01, which gets us a value for our pH of 2.000 if we're being good about sig figs. This number has 3 significant digits, so that becomes 3 digits after the decimal place. So it's pretty simple as long as you recognize what you need to do. Since this reaction goes to completion, that's when we can use stoichiometry. And we can apply exactly the same idea to calculating the pH of a base solution as well. For strong bases, their reaction also goes to completion. They ionize completely. So it will be really similar to calculate the pH of a 0.6 molar barium hydroxide solution. So we need to recognize what the reaction is here. Once again, this is strong, so this is a strong base. It is on our list of strong bases. And the strong bases are the ones we consider strong because they are soluble, that they dissolve in water. And we already know that when an ionic compound dissolves, it splits apart into its component ions. So what's happening when barium hydroxide is placed in water is that it's splitting apart into a barium ion and 2 hydroxide ions. So this is the reaction that's happening when we place this in water. From this point on, it's pretty similar for how we're going to find the pH here. And I'm going to have you pause and give it a try on your own. I just want to point out a couple quick things first. So make sure that you are paying attention to your stoichiometry. Back in the first problem, we had 1 mole of HCl producing 1 mole of hydronium, but we have 2 moles of hydroxide being produced here. And also note that you are calculating the hydroxide ion concentration. So you can't get the pH directly from hydroxide, but you can either use the hydroxide concentration to find hydronium and then hydronium to find pH, or you can use the hydroxide concentration to find the POH and then use that to find the pH. So pause here, take a couple minutes and see if you can calculate the pH of this solution on your own. And I should specify that this is also at 25 degrees Celsius. So the first thing we need to do here is figure out what the concentration of hydroxide is going to be after this barium hydroxide has dissolved. So we're told in the problem that we have 0.6 moles of barium hydroxide per liter. And according to our reaction, 1 mole, we have our invisible 1 over here, 1 mole of barium hydroxide dissolves to produce 2 moles of hydroxide ion. So that means that we would have 1.2 moles of hydroxide per liter. So we can see that moles of barium hydroxide cancels moles of barium hydroxide. So we are left with moles of hydroxide ion per liter of solution here. from this, there are a couple different ways to solve. I'm just going to show one. The way that I would probably do it is to find the POH first, which is the negative log of the hydroxide ion concentration, which is what we just calculated, which is negative 0.079. And then we can use the relationship that pH plus POH equals pKw. Since we are at 25 degrees Celsius, that means that Kw is 1 times 10 to the negative 14th, which means that pKw is 14. So I can plug in my POH that I just solved for, which will allow me to solve for my pH of 14.079. So really similar process, kind of one extra step to get us from POH to pH, but otherwise exactly the same as what we did for the strong acid.